It's time for part two. Part two of how to calculate the volume of a solid of revolution. All right, so quick summary. In my previous video, which probably is going to be called part one, then I explained what a solid of revolution was, and then I explained about the general instructions for how to calculate the volume of a 3D object that spans the x-axis. Okay, so that was the scenario in the other video, and I'm just going to continue that here. But, obviously, I don't think it wouldn't be good to start with this one, and I think that everybody in class probably has enough common sense to start with part one instead of part two. But just fair warning, I'm not going to review all the stuff I talked about in the first video. I did give you these instructions, though, okay? And I wasn't going to go over those again in detail. I was just going to work more problems according to the instructions from part one. Okay, so that's probably obvious enough, but it just makes me feel better saying it. Okay, so let's take this problem here and just go right into it. It says, calculate the volume of the solid of revolution as pictured. So I've got this region here that's two-dimensional, this flat region. It's contained up here by this curve, y is equal to 1 over root 5x plus 6. This vertical line, x is equal to 2. And then down here by the x-axis, and I've shaded it, all right? And I guess over here, like, what would you call that vertical line? The y-axis, or x is equal to 0. So this shaded region is contained by these four things. And suppose that you took that and you rotated it 360 degrees around the x-axis. You would get something three-dimensional. You would get something solid. So I tried to, at some point I'm going to have to leave some of this stuff to your imagination. But what would it look like if you took this and rotated it around the x-axis 360 degrees? Or imagine if this was a piece of cardboard here that I could glue to this pencil, and I spun it around so fast it was just a blur. It gave the illusion of being something three-dimensional. Well, you would end up with something like that, I think. Okay, take this, rotate it around 360 degrees, end up with this. Looks like the cooling tower on a nuclear power plant. All right, but that's what you'd get. That's three-dimensional and so on. So, all right, what is the volume? So the first step is, what are the cross sections? What kind of shape are the cross sections? All right, well, if I could take this three-dimensional shape and chop it up into tiny little slices, they would all be circular. So let's say circular cross sections. Okay, first step of my outline in the other video was identify to yourself what kind of cross sections you'd get. Yeah, so if I took this, and which is made by rotating that 360 degrees around the x-axis, and I cut it into these little tiny thin slices, every cut perpendicular to the x-axis, then I would get these circular slices or circular cross sections. The second part was, what's the area of any cross sections? Well, obviously they're not all going to be the same size, because the slices you make here on this end are going to be smaller than the slices you make over there. They're all going to be circular if you cut it into these little slices, but they're going to be different size circles, okay? So it's going to be pi r squared, right? Because that just, in generic terms, is the area of a circle. And if the cross sections are circular, that's what it's going to come down to. It's just, what's the radius going to be? And the answer is the radius is say the opening right there. How far is it from here up to there? That's the radius of that circular cross section. And if I was to go down on this side a little further, there's this circle there, and there's its radius, and it's going to be bigger. Okay, how do you tell me what size the slice or the cross section is going to be? Well, let's go back to the original picture. This measurement right here, from here to there, determines the radius of the circular cross section that's going to result from rotation. Okay? How far is that? Well, I can't tell you a number. I can't tell you the distance from here to here is always going to be 3. I can't say that. But I can say the distance from here to here will in general be the y-coordinate on that curve. All right? So let's say circular cross sections, and they'll all have radius of 1 over root 5x plus 6. They'll all have the radius being the y-coordinate on that curve. I hope you can see that from the picture. Okay? So, all right, here we go. The area of the cross section is going to be pi times 1 over root 5x plus 6 squared. All right? In other words, a of x is going to be pi over 5x plus 6, right? Okay, there we go. Now, why is the formula that tells you the area of the cross-section, why does it have x in it? Well, because you have to tell me where you are on the x-axis for me to tell you the size of the cross-section at that spot. That's why it's a function of x. So if we were going back to this picture and say, see this cross-section here, suppose this is at 1. Can you tell me how big that circular slice at 1 on the x-axis is going to be? Well, if you put 1 into this formula, it tells you the area of that circular piece at 1 on the x-axis. That's why this is always a function of x. Okay, so third part, let's see. The volume of an object that spans the x-axis is going to be the definite integral from its beginning on the x-axis, which is 0 for my shape, to 2, which is the end of the x-axis. This object would span after rotation from 0 to 2. A of x, so that's going to be pi 5x plus 6 dx. Okay. All right. So anyway, now from here, we have to find a way to do this integral. And the way that we do this, well, I mean, it depends on the integral. This happens to be a U-substitution, all right? And I said at this point in the class, I wasn't going to, just because we've done the integrals so much, I was going to say, well, it's going to be 1 over u du. And I'll tell you that much, and then you can probably handle it from there. If it's that form of integration, then here's the antiderivative. It's going to be pi over 5 natural log 5x plus 6. Okay. All right. So that's what you'll get from U-substitution. The pi is just a constant that's going to be carried along anyway, and you'll get that over 5 part from the U-substitution. Now I need to work this out from 0 to 2. Now you might have noticed about this, you know, math is sometimes all about the details. So you might say, well, the form of that integration 1 over u du, if that's what it ends up being, is natural log absolute value of u. And that's true, but, you know, this thing, 5x plus 6, is entirely positive. I mean, that's just how it's going to work if the x is between 0 and 2. There's no way that that's going to be a negative number if you're living in the world where x is between 0 and 2. So I don't need the absolute value if I know that number is going to be positive. You could, of course, put it if you want to, but you'll see that it's left out when it's not necessary. All right. Okay, so anyway, so this is going to be pi over 5. And let me just multiply like this. If I put 2 in, I'll get natural log of 16. And minus, if I put 0 in, I'll get natural log of 6. Okay. And I think that WebAssign would probably accept that. But just in case, I'll tell you something that I think you should know anyway. Do you remember the rule for logarithms, where subtraction on the outside is division on the inside? Okay, so I could also write like that. This is natural log of 16 divided by 6. Okay, So that's one of the rules, many rules of logarithms. And then I could reduce this, say, by 2 and get 8/3. So I'll give you my final answer. Pi over 5, natural log, 8/3. That's, we should know how to reduce things. Normally the goal is to give the shortest, simplest answer we can with the fewest numbers. And so that would be it as compared to this. So that's the one I'll go ahead and give you as my final answer. Okay. All right. So let's make sure, like, when you watch the video, when you do the assignment, do you see, like, can you imagine how when we take this and we rotate it, we get something that looks like a cooling tower on a nuclear power plant? Okay. And that it would have circular cross sections. Can we agree about that? Can we agree that the radius is going to be different everywhere, but in general, that's how you find the radius? And that, so from it being a circle with that radius, there's the area of any cross section. And from there, the integral takes care of it. That's a formula of integration to find volume from that point. All right. So I gave you that one. I gave you some stuff to think about. Let's see. Let's think about this one. All right. So it says, consider the region contained by y is 3x, y is x plus 1, and x is 0. Okay. Calculate the volume of the solid obtained by revolving this region about the x-axis. So let's see. You don't have to draw the picture to do this, but I think for most people it probably helps. Now, whenever I draw this stuff, I don't draw it to scale. Okay. All right. I just draw it for teaching purposes. I'm not at all trying to do a scale picture. But this is what it looks like. There's y is equal to x plus 1. And that's roughly how it would come together with y is equal to 3x. Okay. All right. And let's see, over here, that's x is equal to 0, because x is equal to 0 is also known as the y-axis. And so we get something like that. And there's the space that it contains. All right. Okay. Now, suppose we took that and then we rotated it 360 degrees about the x-axis. And what's the volume of that? Well, first, can you imagine even what it would look like? All right. So just think about that for a second. I think it would look like that. Okay. We took this. This is the tangible portion. This is the flat part you start with, and you rotate it around. Then I'm thinking something like that. Okay. I noticed about this one that it's hollow in the middle, because this is the solid flat part we start with. Then we rotate it around, and this is what you're going to see on the other side and going all the way around. And it's going to be like totally hollow in the middle. All right. Totally hollow. This part's solid, and it's really, like, without taking a lot of time, not really possible for me to draw like a detailed picture what this thing looks like. But can you imagine like that piece around with this conical portion hollowed out in the middle of it? All right. So that's what we'll be dealing with on this one. Okay. Now from here, say you took this 3D object that I'm trying to do a kind of a brief sketch of there, just to give you an idea. Say you cut it into slices. What would they be? Okay. I'll say that they would be washers. And that comes from the fact that it is hollow in the middle. All right, so what is a washer? Oh, that is a washer. Okay. Where when I'm looking at this part is hollow. So here's the solid, tangible portion of the washer. And then that part's hollow. That's what I'm saying the slices of this are going to look like in general. Maybe like on this end, the solid portion is a little bit thicker and the hollow portion is a lot smaller. And on this end, the solid portion is thinner and the hollow portion is a lot bigger. But they're all going to be washers. All right, so I need to to see that you can imagine that, yes, we are going to get a washer if we do this. And a washer is like, you know, two circles, or it has an inner radius, which I'll call R1, and it has an outer radius, which I'll call R2. Okay, so that little circle there, that's the hollow portion, is going to be a circle of radius R1. And then this larger circle out there, that's going to be a circle of radius R2. Okay, and because it's just, you know, one circle minus another circle, it's going to be the area of the larger circle minus the area of the smaller circle. And that will amount to pi times R2 squared minus R1 squared. Okay, so that's how we find the area of a washer, or that's what a washer is, and that's how we find the area of it. So if you could cut this shape into slices, just chop, chop, chop all the way through, knife perpendicular to the x-axis, and the slices they're going to appear like this. You know, something like that all the way through. Different size, different aspects, but a washer all the way through. Okay, so they're going to be washer cross sections. Now, what is that larger radius? So let's go back to our shape over here. There is the thickness of the washer cross section that's at that spot. Okay, there's going to be a ring that goes all the way around. That's the washer that we cut out right there. So the outer radius is going to be this, and the inner radius is going to be like that. Okay, so you could say then that the outer radius of the washer cross section, say the one that goes right here, that slice that we cut out of it right there, okay, see it? Then the outer radius is going to be the y coordinate on that line. So R2 is going to be x plus 1. Okay. All right. I can't just tell you, oh, the outer radius is 4. You know, because how far it is from here to there depends on where you are on that line. You tell me the x coordinate, this is that outer radius. R1, that inner radius, is the distance from the x-axis to this line. Okay, we're on that line, the y coordinate is 3x. So the inner radius is 3x. So can we agree then? We take that original region, we rotate it around the x-axis 360 degrees, that we will get washer cross sections. Every slice is going to be one of these, and that will be the area. That will be the inner and outer radius. Okay, second part, 2. What is the area of any cross section? Well, now that I know it's a washer and I know each radius, each radial aspect of it, then it's going to be pi times the outer radius squared minus the inner radius squared. Okay? Now, I think we might as well work on that a little bit before we try to do any calculus with it. All right? So let's take pi and let's just multiply all that out and get like terms and so on. We'll get x squared plus 2x plus 1 minus 9x squared. So what we'll get out of it that we'll use in the next step is going to be negative 8x squared plus 2x plus 1. Okay. Now, all right, so we got the whole setup, I think. I got my shape. I know how I rotated it. Identify my cross sections. I tell you the area of any cross section. Why does that have x in it? Well, you have to tell me where you are for me to tell you exactly how big the cross section is. That's why there's an x in that formula. 3 was that the volume is going to be the definite integral of this a of x thing. Okay, so pi negative 8x squared plus 2x plus 1 dx. Okay, did we forget something? Well, we need to know the bounds of the integral. What are the bounds of the integral supposed to be? The bounds of the integral are the span on the x-axis. Well, okay, so this shape starts at 0. Where does it end? Where's that point? Let's see. Well, that point would be the intersection of the lines y is x plus 1 and y is 3x. So let's say, well, we need to find the point of intersection between those two lines to find our upper limit of integration. So we can set them equal to each other and say, what point does x plus 1 and 3x have in common? Okay, so we do that, we'll get 1 and we'll get 2x, and so we'll get that x is a half. All right, so these two lines meet each other at a point with an x coordinate of a half. All right, so that point right there, 1/2 for x. Whoops, I put 1/3. 1/2 for x. And what's the y coordinate? Just to make sure, these should agree. What's 1/2 plus 1? That's 3/2. What's 1/2 times 3? That's 3/2. So that really must be the right answer because they do agree with each other. So that's 3/2. That's the x and y coordinate at that point. The x coordinate is what I need for my integral. It spans the x-axis from 0 to a half. So then I put 1/2 up there. All right. So now this should be an easy integral to do. Pi is my constant there. I'm just going to carry it on like so. And I'll get -8/3 x to the 3rd power plus x squared plus x. All right. And I got to do that from 0 to a half. So, okay, I'm going to get pi. Let's see. I think any normal person would do this by calculator, but let me see if I can. We should know how to do math, shouldn't we? All right. So 1/2 3rd power, that's going to be 1/8. The 8th will cancel, so I get 1/3 negative plus 1/4. If I square it, plus 1/2. And I'm going to put these out of 12. And so, let's see, 6, 3, that's 9. And 4, so I'm going to get 5 pi over 12. All right, 5 pi over 12. That's it. That's how you do it. Now, this is like the other problems, but we haven't seen a shape that was hollow, and therefore we have washer cross sections. That's what makes it different than the others. Okay. Otherwise, same thought process. I still think you have to have a little bit of an imagination about what the shape is actually going to look like. If I can't convince you that, look, this shape is hollow, and if you cut it into tiny little thin slices, they're all going to be washers. They're all going to look like that. Then, like, we're getting off to a rough start. So if that's the part you're having trouble seeing, then that's something that we should talk about in more detail. All right. If you can get past that, you're probably okay. If you can get down to this part, you're probably okay. If you're having trouble getting started with steps 1 and steps 2, then, that I can make a video in more detail about just that if you want to. Okay, let's do one more. Okay, and I make this one even different than the others. So it says, suppose we have a region. We always start with a region, a flat region, a two-dimensional region. And this region is bounded by y is equal to x squared, x is equal to 0, and y is equal to 1. Okay? So far it sounds the same. And it says, calculate the volume of the solid obtained by revolving about the line y is equal to -2. So this time we're not taking that revolving about the x-axis. We're taking it and we're revolving it about some other distant line. Okay? All right. And so what would that be? Well, I mean, my picture's not to scale, but I don't know. Let's see. Something like this. Kind of like down here, like that. Okay, and then it's going to be like, oh, this reminds me, like, I don't know, if you've ever been to like a museum and you can make a donation and you like roll a penny down this like whirlpool looking thing and it ends up down, yeah, it's kind of like that. I don't know what that's called, but it kind of looks like that. That's a really sorry picture, but it's, for now, that's the best you're going to get. If we rotate this around that line, then that becomes the center axis. And like those distances are equal, okay? So we're not revolving it about the x-axis, we're revolving it about this other distant axis, y is equal to -2. Now, can we agree then that this has something in common with the last one? You take this solid portion, rotate it about that line, then that whatever you want to call that shape, it's going to be hollow, all right? So like, can we agree we're going to get washer cross sections? For sure. If you take this 3D object and you cut it into those little thin slices up and down, every one of them is going to look like this. They might be thicker or thinner or bigger or smaller, but they'll be washers. Okay, washer cross sections. Now, here's what might be the tricky part. If I was going to cut like right here, I was like, I hold my knife there, totally perpendicular to the axis of rotation. I cut this little slice out. There's the thickness of it right there. That's that washer part right there. That's how thick it is. This would be the inner radius, and that would be the outer radius, okay, of the washer. So, so if here's my cross section, from here to here, that's the size of this hollow circle in the middle. That's the radius of it. From here to here, that's the radius of this outer circle. And I know this washer is not big enough to match up with my picture, but we're going to have to use our imagination a little bit. All right, now, so let's find R2 first. Let's find that outer radius. How far is it from here, this line, y is equal to -2, to here, this line, y is equal to 1? Now, this is a horizontal line. There's no slope to it or anything like that. It's not curved. It wouldn't matter where I drew this. Isn't the distance from here, y is equal to -2, up to here, y is equal to 1. Isn't that just 3? I mean, if this line is 2 spaces under the x-axis, and that line is 1 space above it, they're 3 spaces apart. That's just how it is. Okay? Now, I suppose you could see that as take the y-coordinate on that line minus the y-coordinate on this line, if you wanted to. But I was hoping you just, that's 2, that's 1, there's just 3 apart, okay? All right. Now, normally I say about this, I say, well, I can't tell you a number for that because it's different everywhere. Like when we did, I don't know, let's take this one and say, well, I can't give you a number for the radius because, like, how far it is from here to there depends on where you are on the curve. Well, that's because it's a curve. Here, this is straight and horizontal. It's always one distance up to that line. That's what a horizontal line is. But nonetheless, so the outer radius of the washer, cross-section, is 3. What's the inner radius? What's the small radius? So R1 is the distance from here to there. Well, that is curved. The distance up to there varies. It's a lot further up to this curve the further to the right you go. Couldn't we use the same principle, though? Couldn't we find this by taking the y-coordinate of our top minus the y-coordinate of the bottom? 1 minus -2. That worked for R2. Why wouldn't it work for R1? So let's take x squared, which is our y-coordinate, our vertical coordinate on that curve, and we'll subtract the y-coordinate down there. It's going to look like that, okay? Let me put in parentheses again. Then I'm doing x squared minus -2. So I did both of these the same way. I think the 3 is a little bit easier to understand, but I did them both exactly the same. All right. So I've got washer cross sections for this 3-dimensional shape. Second thing, I can tell you the area of any cross section because the area of a washer is pi times the outer radius squared minus the inner radius squared. On my picture, you see the outer and inner radius each marked, okay? All right, so let's do a little simplifying on that. to make it easier to work with in the next step. So I see pi, so I get 9 minus x to the 4th minus 4x squared minus 4. Okay, so here's what this is going to be. Let's just leave this pi out of it. That's a constant. We don't need to get that all mixed up in there. So we'll say minus x to the 4th minus 4x squared plus 5. All right, that's what our a of x, our area of any cross section of this, is found that way. I said it before, I'll say it again. Why does that have x in it? Well, because every cross section's a washer, but they're all different sizes. You tell me x, you tell me where you are on the x-axis. This will calculate the area of the cross section at that spot. Okay, so 3. If you want the volume of this, then find the definite integral from 0 to 1. Why 0 to 1? These two things, x squared and y is equal to 1, happen to intersect each other at the point 1 and 1. Integral of 0 to 1, pi negative x to the 4th minus 4x squared plus 5. Okay, so here's what we're going to end up doing. We'll take pi times this evaluation, negative 1/5 x to the 5th power minus 4/3 x to the 3rd power plus 5x, 0 to 1. All right, so it's going to be pi times, let's see, we'll get negative 1/5 minus 4/3 plus 5. That's all we're going to get. The 0 is not going to give us anything. Who's besides me, is anybody going to do this on paper? I'm going to go ahead and do it on paper. I think we should be able to do that. Common denominator is 75 here, or 15, I'm sorry. And so we're going to get negative 3 out of 15 minus 20 out of 15, and then plus 75 out of 15. That's how that's going to work. So we'll get 52 pi over 15. That's what we'll get, right? Okay, don't forget about that pi. 52 pi over 15, that's volume. Be like feet to the 3rd power, cubic feet, cubic centimeters, something like that. All right. So I showed you 3 problems that were different. I give you considerations for all of them, but we got introduced in this video to what a washer is, and a washer is just what you think it is. It's one of these. All right, everybody's seen one of these before, probably. If you haven't, now you have. But this line of distant rotation, that makes this one a little bit different. You know, I might have you focus on this part. Why did I find the inner and outer radius like that? Put some thought into that. If you're okay with that, I think you're in good shape. If that's not so clear to you, you might have to put some more thought into it, or you might have to ask me to look at other examples that are like that. Nonetheless, go through the same procedure as the other problems from there. We get 52 pi over 15.